Thing like that?
Yes, actually, yeah, and it's right after this class, so that would be good. I have another meeting to attend to, so if you wanted to stick around and talk to the students, that'd be fine. I'll probably come back on and just stop the recording. Um, but yeah, my usual office hours is 10:30, 11:30 Wednesday.
Okay, and on Wednesday only or on Monday also?
Just Wednesday, and then Yunran is picking up an hour on Fridays. So
Got it.
yeah.
Okay, and everybody knows how to get hold of me anyway. If you have questions, don't hesitate. So pretty easy to find me. Anything else? So we just go ahead and start sharing? Is that the...
Yeah.
I haven't done a lot of this Zoom. You know, I was lucky, I guess. You guys, some of you guys last year were the last consulting class I taught. I turned it over to Mary in the spring. And so I dodged having to move everything online with a week's notice. I thought everybody did a terrific job of that. So I don't have a huge amount of practice at this Zoom teaching. So I've done one or two guest lectures like this. So if you think there's anything I should be doing, I'm not. Don't hesitate to let me know. So I'll just start screen sharing and go from there. Okay, it's usual deal. If anybody has questions, just interrupt. I mean, you can raise your hand and such, but it's so hard for me to spot that. So just jump in and start talking, ask me questions, just fine. Anything else before we start? Okay. Let's see, I need to make this full screen now somehow. Well, maybe not. Maybe I'll just leave it as it is. Okay, everybody see my screen?
Yeah,
make sure to get all this fumbling around recorded, Matt. Wouldn't want to miss that. So, okay, so let's just start a little bit here and talk about a data set, and then we'll go into the outline and such. But I thought we might take a look at a data set here that in this you'll see this again over the next couple of days. That I'm actually over all 3 days that I'm in here. I'll be talking about this data set, so we'll get a little experience with it. It was a study about cereal consumption, and it was when I worked back in the nutrition center years ago, and they took the idea was to give an intervention, some sort of a like counseling intervention about trying to get people to eat more healthy cereal. And so there's a condition which is 1 for the experimental group and 0 for the control group. And then they selected children who were overweight and enrolled the child and all of their family members. So that's what you see here. 3, the indicator 3 indicates the child that was selected into the study, and all these other numbers, and then 1 is the family. So there's these first 5 people were in one family, the next 4 were in the next family, the next 2 in the next family, and so on. And then these indicators are the family members. So these are 1 and 2 are the parents. I forget which is the mother and which is the father. Then 3 is the kid that was sampled, and 4, 5, 6, 7 on are the other kids in the family. So that's the way the data are coded. And then C1 up to C, I believe, 14. Now there's a couple covariates out here at the end: weight, height, age, and sex. And then here are the outcome data. So the first subject on the first week had 7 servings of cereal. And on the next week, that same person ate 5 servings of cereal. Everybody good with the data? Questions about what anything means?
someone had 24 servings of cereal in a week.
Yes, maybe they're like me. Maybe they have a bedtime snack of cereal, and when they can't find anything else interesting, they grab some cereal. I think, as I remember, a serving was something like half a cup, so it wasn't extreme amounts. But so yeah, let's. Any questions about the data?
Is there a distinction between cereal types? Like I'm sure Wheaties is better for you than Lucky Charms, although the latter is much more delicious.
Yes. No, and I've forgotten. This was more than 10 years ago, so I've forgotten all the details of it. And they're, but for this purpose, no. Yep, for our purpose, no. What else? Anything? Okay, so why am I talking about this in this? Why am I talking about this data set in Matt's class on longitudinal data?
You have some nesting here.
Sorry?
You have nesting within family.
Yeah, we have nesting within families, in other words, correlation. So the subjects, the people in a family, I mean, so the idea is the clustering or the nesting, there may be families that just like cereal and they buy a lot of cereal at the grocery store, and they, you know, kids tend to eat what their parents eat and things like that. So that would be a high cereal eating family. The next family may have very little cereal eating. Okay, that's one. There's a clustering by family or correlation of members in the same family. What else? Okay, let's take a look at this subject, number 8. And let's take a look at this subject, number 13. What do you see as difference about them? 8 loves cereal, and 13 isn't not so fond of cereal. Okay, what do we call that kind of correlation? Measurements on an item that tend to be more similar than measurements on different items. Well, isn't that the very same? Sorry, go ahead.
Like a repeated measures within a subject?
Yes, repeated measures. So okay, so this is interesting. There's two things going on here with repeated measurements. One is that the measurements on an individual, on one person, may be more similar than measurements on another person. And that's what we see here. So these numbers on number 13 are all pretty small. These on number 8 are all pretty large. Okay. Isn't that the very same thing that we just saw with families? Family members tend to be similar to each other, and measurements on a subject tend to be similar to each other. So this is actually the same kind of correlation, but now at the lower level, right? Measurements on an item are more similar to each other than to measurements on different subjects, okay? Everybody see that that's the same kind of correlation? Clustering, item measurements clustered on the same subject, okay? Everybody okay with that? Okay, there's one more thing going on here.
If you look at,
Sorry, I just want before, and then I'll get your question. There is a difference though between this situation where these measurements are measured over time on the same subject, and these measurements where they're measured not over time, but just clustered on the same family. Now go ahead with your question.
oh, I was going to say, like, if you look at observation 14, that it seems like the 4th week is more like highly correlated with the 3rd or the 5th. Like if I start eating cereal, I get like addicted to cereal and that's all I want. And then eventually I'm sick of it. So then maybe that's what happens at like week 7 that they drop to 2.
Exactly. Yeah, exactly. Now, can you have that kind of correlation with the members of a family? Not really, right? You can't really have that sort of correlation. I mean, you know, maybe have siblings that are closer to each other and they tend to eat, but you don't have a variable to record that. Whereas with time, you do have a variable. Okay, so that's another kind of you know, a correlation just means some things are more similar than to each other than to other things. Okay, but there's different kinds of correlation. There's the clustering that we saw, and there's also this time correlation. I couldn't see, and on my screen it doesn't pop up who's talking. I think there might be a way for me to adjust that, but I'm not going to try now. So, so yeah, these measurements that are similar to each other, that's called a series correlation, or a repeated measures correlation, or a temporal correlation, or it's also called serial correlation. And you know, I had talked about this data set in class for years before I realized somebody pointed out that pun to me, that it is actually serial correlation. So unintended, sorry about that. But anyway, that is another kind of correlation, okay? And we see that, that kind of series correlation. Another kind, where's the place we see it pretty much every day? Look out the window, right? Tomorrow's weather probably will be similar to today's. And there will be patches. When it cools off, it tends to stay cool for a few days. And then when it's hot, it tends to be hot for a few days. Okay, so it's exactly the same thing. Nearby days, measurements that are nearby in time, are more similar to measurements that are far away in time. Okay, all of these things are different kinds of correlation. Everybody okay with all the correlation going on in this data set? I thought it was kind of a nice example of you know, the concepts you've seen here. And, you know, those of you who took consulting from me last year, you remember we talked about identifying the structure of a data set. And one of the things when you ask statistical questions is to understand the correlation structure of the data. And there are two real common kinds of correlation. One is the clustering and one is the series correlation. They're seeing them both in here, okay? So just a little review from a year or so ago. Anything else on this? Okay, so that's
Are the blank observations?
sure. I didn't hear.
Are the blank observations? Are the blank observations 0 or missing?
Yeah, those are missing. Yep, good, because there are some zeros here. These are actual 0 when no cereal was eaten. That's a great point. Those are actual 0 measurements, and these are no data collected missings. Yep, good. What else? Okay, so that's why I'm talking about it in Matt's class. Why am I talking about it today? What is it about this data that looks a little different than other things you've seen?
Is it count outcome? So it might be Poisson.
Exactly, it's counts. We're counting things. And so that's why I'm talking about it today in the section on non-normal data. Okay, everybody good with that? So if we might talk a little bit about options for analyzing count data. I don't know if you've had much exposure to it, but some of the things we've talked about in the past, count data, but also what comes along with count data, it's also not negative, right? Can't have negative counts, so it's more than just integers. We can't have negative counts. So what options do we have for analyzing data like this? We're a little bit limited. You know, you could use a normal approximation, but usually things that are non-negative are also highly skewed, and you can kind of see some of that here. If you look through the data set, tends to be a lot of kind of average observations, and then you get a few of these that are like somebody pointed out the 24 and the up in the 16s and 17s, so you just get some skewness as well. So those are all things we need to cope with. What's one tool we talked about in the past of ways we handled skew data?
Transforming the data?
Yeah, we could transform it, and the most common transformation is logs, right? And how will that work here?
That would be problematic because of the zeros. So you'd either have to add one to everything or find some other way.
Exactly. Come up with something, and that's something. Anytime there's still a remaining somehow, you don't quite have it figured out. So that's kind of where we are now. So what I want to talk about today is the modern method for analyzing data
I have
like
a
this.
question, Gary, about the transformation.
Sure.
So typically with count data, your skewed is going to be left skewed. So the clustering is on the heavier side of the distribution, and usually log transformations don't really do a good job at transforming those types of skewed data. What
Yeah,
other transformations would you apply to something like that?
that's a great question. The old-timey way to do this was called variance stabilizing transformations, and you can do a few calculations and work out what transformation makes the variance relatively constant across all the observations. And it turns out for a Poisson distribution, which would be an option for this data, it turns out the variance stabilizing transformation is a square root, which is also nice because the square root of 0 is perfectly fine 0. So it solves both of those problems. However, it's not very nice to interpret. It doesn't have a nice interpretation in the sense of an absolute change or relative change or a percent change. A square root is just not a very nice way to state the results. And so that's a downside of that.
A follow-up to that is if you take the square root of some of these values, you're going to get decimal points. You no longer have integers. How would you model that with a Poisson?
Well, that's actually okay because using the variance stabilizing approach, you would not use a Poisson. You would use a variance stabilizing approach and then treat it like normal data.
Okay.
Just treat it like regular old numeric data. And Poisson would never enter it. Well, Poisson would enter it in the theoretical calculation of what transformation to stabilize the variance. But once the transformation is done, never look back. You don't pay attention to whether it's Poisson or anything. You just treat it as normal data. Yep.
Okay.
Yeah, good point though. What else on this? Anything? Okay, now I'm going to tell you what I'm going to start talking about the actual content of today, which is generalized linear models. And I don't think John Rice in the spring talked about generalized linear models. He talked about logistic regression quite a bit, right?
We did do some Poisson.
And a bit of some Poisson and some logistic, quite a bit of logistic, is that right?
Right.
Okay, yeah. Okay, so what we're going to do is talk about a big umbrella, generalized linear models, a big umbrella that includes those two, normal, gamma, exponential. I mean, it's really a huge class of models. So that's what we're going to talk about, modern way of handling this kind of data. So when we were back in the olden days, when we were all in a classroom and had blackboards to write on, I would have written something like this in the corner of the board, and this is what I plan to work through today. I'll do some talk about the basic theory. First, I'll develop the ideas of the models, then I'll do a bit on the basic theory, some data analysis. In order to do data analysis, you have to fit models, estimate parameters, check assumptions, stuff like that, and interpretation. Then I'll kind of end, I think I'll have time today to end with a bit of history and some of the key references on this. So, and then today, this is a detailed listing of what I'll do today, and then next time, which will be next Monday, I'll talk about these extensions of Poisson. Really, Poisson's a pretty limited distribution, so I'll talk about some extensions of that. So that's my plan. Other questions before I jump in?
Are you sharing the document? Because we still see the Excel spreadsheet.
Oh, I see. This is, okay. So I thought I was sharing my screen. It looks like I'm sharing up specific document. Thanks for that. Let me try this again.
I think maybe if you unshare your screen, then start sharing again, you can pick.
There it is. Okay, there it is. Okay, so it's going to take a little more jumping around than I thought today, but now that I get the hang of it, maybe get the hang of it. Okay, now you're seeing the outline. Okay, so that's the stuff and you have this document, is that right? Matt said he would post it on Canvas. Yeah, so you'll have this part. So here's what I would put in the corner of the board, and here's the detailed outline. So I've done number one. I'll just start in with some of these others, and now I have to unshare and share again. So Matt told me last night, kind of late, that he makes slides and all this. So I'm going to make him look really good today by comparison. Sorry about that. But I did go through and highlight some of the things I really want to mention specifically today as I talk about it. And again, don't hesitate to interrupt me. This is just a more detailed version of what I had before. So we'll do up to 3.8 today, and then 3.9 it will be next time. So just to summarize what I've said before, today I'm talking about variables that are not normally distributed. What we'll see, though, that's a little of an overselling, because it's not just any there's one normal distribution, but there's lots and lots and lots of non-normal distributions. We're not going to handle, these methods I'm talking about today don't handle every kind of non-normal distribution. They handle a very specific set of non-normal distributions, ones that can be described by exponential families. So this is, when I say non-normal, it's pretty, possibly a little bit misleading. So this first paragraph talks about how these methods can be also extended to correlated data, which I think Matt will come back and do a couple weeks of after I'm done. Let's see, a couple different approaches. So yeah, the other options, actually, I just talked about this option here. Sometimes data that are counts, if they're large counts, they may actually be pretty well approximated by a normal, and you may not have to fuss too much with this. If not, you can try transformations. Sometimes those work. Down here, I think what I mentioned is that there are interpretation issues, and one of the things about a generalized linear model is that the interpretation tends to be really nice. There tend to be really nice interpretations of results. So I think that's another benefit. So here's some examples. So most of these are from Matt's National Jewish Work. So I wrote this section, and then Matt tidied it up, added a lot of good material. So it's kind of a combination of our stuff. So we have a few things here. Say if on number one, if your outcome is slightly right skewed, can't be negative, and really not much chance of it being zero, a good option here could be a transformation, a log transformation, or even, depending on your purpose, could be just modeling it as normal. It's not that non-normal. What tool do we have to help us out when the data are not normal? Which big theorem?
Central limit theorem.
Yep, central limit theorem says averages tend to become normal as you average more things together. And it's much more general than that. It turns out that regression coefficients and things like that also tend to become more normally distributed. So we can actually use things like the 95% rule and inference and Wald test and such. So that would be an option here in number one. How about number two? Moderately right skewed, non-negative, but still not any real chance of zero. What option do we have here?
A log transformation.
Yeah, we could transform for logs. And logs actually have a pretty nice interpretation on a percent scale. So that would work fine. So at least we have a possible solution. Here's one where right skewed, but now there is a pretty substantial possibility of zeros. This is one we don't have a ton of good options for, and I'm just going to next time mention some options like a mixture model that models, say, the positive part as exponential or something, and the zeros as binary, and combines those two models into a two-part model. So I'll talk about that a little bit next time. Number 4, whether a child had an asthma exacerbation in a given week. How would you handle that?
Logistic.
Yep, it's a binary example of binomial, so you can use logistic regression. 5% of patients that adhere to doctor's directions got a large N. So this is the percent of each physician's patients. So if you have a large N and kind of a moderate P, you could get away with just normal modeling on this. And you might not be too far off. Another thing you could do is you could also do logistic regression. You could treat this as binomial, do logistic regression. Number 6, number of times an inhaler was used to treat asthma. These are small counts, mostly zeros, ones, and twos, but sometimes I think when Matt and I looked at this data set, wrote a couple papers with it, I think the maximum number was 6 over several thousand observations. So, which makes sense, kids are not using their inhalers more than a few times a day. How about this for modeling?
On or negative binomial.
Yeah, but let's talk about, exactly right, but let's talk about some of the other options. We could just use normal, but how do you feel about that? That's going to be a pretty terrible approximation. These are counts. There's only 7 possible values. They're discrete. They're not negative, and they're highly skewed. Okay, so this is getting very non-normal. Okay, so that's not going to be a great option. We could transform, except
We have zeros.
all those zeros, right? So that's not going to work. We could add something to it, but again, there's a something and that's not decided. And it turns out it actually does. In a case like this with a lot of zeros, it actually does make a pretty big difference, or can make a pretty big difference to results, what you add. So we don't really have good options here. I think number 6 is maybe a good one to keep in mind for a case where we really don't have. 6 and 4. Are good cases to keep in mind for why we need some good tools for this, because we're pretty well stumped for any of the options we have.
For number 6, where there's thousands of participants, could we use an ordinal logistic regression model?
Oh, that's a good thought. Yeah, you could do that. You start to get some challenges with interpretation. Well, actually, let me put it differently. The interpretation is quite different. So the interpretation of ordinal logistic regression would be something like the odds ratio for, well, you could model it that way, and then you would get odds ratio, results would be odds ratios. With a count, say a Poisson or negative binomial type model, your estimates would be rate ratios, so they'd be more on a percent scale. So let me just say those are different interpretations, and depending on your situation, you may want one as opposed to the other. Yep, that's a good point though. That would be the best non-generalized linear model option that I can think of. Yeah, so good. What else? Other questions? Okay. So now we'll talk about generalized linear models. I'll do a little motivation and such. So this is the approach based on exponential family. And so there's two ways to think about this. Actually, let me get into notation. I'll tell you a mention of history here. So there were a few attempts, there have been a few things, specific models published before, say, 1970, but really there were two barriers. There was no comprehensive theory of how to handle data like this. There were specific cases, like logistic regression was one, Poisson regression was another, but there was no real recognition that these were special cases of a bigger class of models. The second thing is that, as we'll see later, these models are not as easily fit as, say, a linear model. A linear model, you need matrix calculations. You need computing software that will do matrix calculations. For generalized linear models, you need computer software that will do iterative matrix calculations, and it's a step above. And so the computing at that time, I mean, there were very few statistics packages around. There was not a lot around. So you don't have to go back far. I mean, 50 years in the development of a discipline is not that far. And if you go back that far, this really didn't exist. And with this one paper, Nelder and Wedderburn in 1972 really created this field. It's a fun paper to look at because so much of the notation really still, and the ideas and everything really still is there. So it's good to take a look at. The notation, I said the notation is very complicated. I don't know. I mean, it is, I think, it's a step above linear model notation, and there are a couple twists which I've tried to highlight here. Some of the things are pretty standard. Y is the outcome, X is your covariates for subjects, betas are your regression parameters. Here's where it gets a little trickier. There's mu is the mean outcome, which is actually pretty easy to remember. Mu for mean, so it's not that hard. Eta is kind of standard notation for what's called the linear predictor. And I think John probably used this terminology in logistic regression, maybe in Poisson regression, linear predictor. That's your linear combination of covariates. So that's your outcome, that's your, all your treatments and your stratifying variables and adjustment variables, and things like that. So those two keep an eye on, because those, I think, are the two new pieces in this. And then the link function also is, you would have seen that in transformations, but it's used quite differently here. Other things, these are very specific to exponential families, so I'll get into this stuff. We won't need the bottom ones. We'll need likelihood, but not some of the others. So any questions on the notation? So I'll remind you, those of you who took theory, this will start to look pretty familiar, exponential families. So you would have seen it, and so I'll point that out too once we get down there. So so this little z here, I kind of like to put that in. I think I might be the only one, so I don't even know if I've converted Matt yet. So I like to put it in because GLM can either mean general linear model, which means normal, or generalized linear model, which is what we're talking about today, and it's not clear, so I like to put the Z in, but like I said, have not had too many conversions yet on that. So here's, let's talk, any questions then about the notation? Okay, so let's talk through the motivation, and this is a really nice way, I think, to think about how generalized linear models came to be such a natural extension of normal models. And by the way, I mean, pretty much my whole career, I've looked at unusual data, non-normal, exponential family type data, and I have learned so much about normal modeling from studying non-normal models. It's really interesting how you see You see which parts carry over easily to the non-normal case and which parts don't. You kind of see where things break. And I think you can see that here. You'll see that as we develop that you know, parts look exactly like they did in a normal model and other parts are quite different. So just point that out. So here's a good example to keep in mind, number of visits to an emergency room each day. What would be a good sort of, well, actually, let's just think, we'll think through that here. We could try this model here. And the problem with this, so this is just a regular linear regression. Okay, it's linear because this is linear in the parameters. It's got an error term. The difficulty is there's no way to choose epsilon so that your outcome is what is on the space you want it to be on. So for instance, if it's a count, how do you choose x prime beta is what, x beta is what kind of a number? It's just a continuous number, right? It can be positive, negative, fractions, okay, so there's no pattern to that. How are you going to come up with an epsilon to add to that so that y is a count? Okay, so that approach just doesn't work. We're stumped at the first thought. As I think I talked about the variance stabilizing transformations. We talked about the limitations of those. So right here, if there's a key idea in development of generalized linear models, it's this right here. Here's a model, a normal regression model. And here is a different model based on on a normal distribution. How do those models differ? If you were to simulate data from those models, how would they be different? Well, they wouldn't be at all. Those are two identical ways to write a normal distribution, right? You can write a normal distribution, say y is normal with mean mu and variance sigma squared, or you can say y is a standard normal times sigma plus mu. And that's really the sort of exactly what we're doing here. But as soon as that's recognized, up here in this model, how would we make the step to Poisson? We can't just say epsilon is going to be Poisson because x prime beta is not an integer, so we won't get an integer outcome, right? So that approach won't work. But look at this. How about if we just changed n to Poisson? Okay. Now your outcome is sampled from a Poisson distribution. Its sample space has to be 0, 1, 2, 3, 4, and on, right? So we've got the right sample size, sample space. Everybody see that? You see the benefit and the fact that just by rewriting this normal model, we're able to now generalize it to Poisson. Everybody okay with that idea?
We are assuming the variance is the same as the mean there to make it a Poisson.
Yes, that is a fact about the Poisson. And that'll become important in a few minutes also. Good. What else? Okay, so we just hit another brick wall though. We went around the first brick wall we hit, but now we hit a second one. What's the problem with this model at the bottom of the page here? Well, tell me what x prime beta looks like. It's a number, right? That's all you can tell me. Could be a fraction, could be 0, could be negative. What do you know about a Poisson distribution? How many parameters does a Poisson have? 1. Right? And what can you tell me about that parameter?
It has to be a positive count.
It has to be a positive number.
Integer.
Not quite. It's the outcome that's the integer. But the mean of the distribution can be anything, right? Can you have a Poisson observation that's 2.3? No. Can you have a Poisson distribution with a mean of 2.3? Yes. Do you see the difference? Okay, and that Poisson distribution with a mean of 2.3, can you generate any values except integers? No. Okay, everybody got that? Everybody okay with the difference? By the way, these are crucial concepts. Let's review them a little bit. So there's the sample space of a distribution. This is general for not just Poisson. Any distribution has a sample space and a parameter space. What's the sample space mean? It's the set of possible values of that random variable. Okay, so what's the sample space of a Bernoulli distribution?
0 and 1.
0 and 1. What's the sample space of a Poisson distribution?
0 to infinity.
0 to infinity integers. All right. Okay, sample space of a normal is any real number. Okay, what's the parameter space of a Bernoulli distribution?
One.
No, it's the continuous range between 0 and 1. Okay, what's the parameter space of a Poisson?
Zero to infinity, continuous.
0 to infinity, continuous, and not including 0. I guess 0 is some sort of degenerate case, but we wouldn't think of that as being a real case. Okay, so you get the difference between the sample space and the parameter space. Everybody okay with that? Okay, so what do we have here at the bottom? We have y, which has to be, is drawn Poisson, so it has to be a non-negative integer. And we have x prime beta, which if it's going to be the mean of a Poisson, it has to be positive value, right? But there's no way to constrain it that way, okay? So we need one more step to construct this model. And here we go. And this is a super useful trick every place. If you want something to be negative, if you want something to be positive, look at its exponential. And this is useful in numerical optimization. If you want to optimize, you can do constrained optimization, but it's much easier to optimize on the parameter e to the beta and then transform back. Numerical trick. So in here, it's not a numerical trick. Here, it's really a fundamental part of the model. Okay, everybody get this? Everybody see the idea here? So now, what's the problem with this model? None. We're really there. Okay. What do we know about this mean of this Poisson? It is continuous, non-negative, continuous positive. That's what it's supposed to be. What do we know about the y? It's always a positive, non-negative integer. We've got it. This is Poisson regression. Okay. But that's the sequence of thinking that I like to use about why this is such a natural way to extend the normal distribution to exponential family. Okay, anybody have questions about this? Sometimes written a little differently. Sometimes it's written like this, Poisson mu, emphasizes that mu is the mean of the Poisson. And mu is defined as log of the linear predictor. I kind of like this way just because it reminds me there's an exponential, everything's positive. I can see the mean right there, okay? Any other questions on that part? Okay, so G is called this link function, and that's really why this is written this way. It just seems, so the link function for a Poisson is not the exponential, it's the log. And this has to do with the theoretical, the way things are written. That actually could have been the other way. The log, so log here is the link function, exponential is the inverse link function. There will always be a pair like that for a generalized linear model. So that's in general, that'll be our G is the link function. And this model then is Poisson regression. So in more generality, the mean is the inverse link of the linear predictor. X prime beta is our linear predictor, right? All the covariate information. Any question there about that stuff? Okay, there's another graph I want to show you. There's one on the next page down there, which is all fine. Let's see. I'm going to wait a few minutes on those graphs. I mean, these are functions of the plots of the link function. You can see that there's one of the nice things a link function usually does, not guaranteed, but usually does is keep, or a desirable link function keeps the model parameter in the correct parameter space. So exponential is always positive for Poisson. Inverse logit function is always between 0 and 1 for logistic regression. Okay, so that's a feature of what's a nice link function. Everybody good with those things? You talked a lot about logistic regression. Just to point out, actually, I'm going to go down a little bit and point out that there's a special case. Other question. By the way, there's no, this is the standard, I will mention this. This is the standard Poisson regression here, but it's not required. You could use this model, in fact, and I have fitted this model before in published papers. If I want a linear interpretation for my covariate effects. It's not common, and you can get in trouble if X beta goes negative. But if you have a situation where it doesn't, it can actually make sense. The standard is the log, but you can have other options. Let's see. Okay, so this key idea, section 3.4 is a really key idea. This next little bit is really the wrap up of what the motive. So what I just did is motivate this whole thing, try to make it seem natural. It's a little easier to remember things if they seem natural. But what I want to do now is wrap things up. So in general, a generalized linear model looks like this. Y follows some exponential family distribution, and I parameterize the distribution in terms of its mean mu, which is the inverse link of the linear predictor, and possibly some other parameters. And so if you look at this, there's really three things we have to specify. There's a random component. We have to say which distribution it is. Poisson, binomial, normal, gamma, whatever. Those are the most common ones, but there's some others. We have to specify the random part. We have to specify the systematic component, the linear predictor. That's all your covariate stuff, your treatments, your time trends, all that stuff. And you have to specify the link function, which is really the specifying the scale of your analysis. Do you want to be on the linear scale? Do you want to be on the log scale? Do you want to be or percent scale or logistic scale? Okay. But those three things, we'll see. If you want to specify a generalized linear model, those are the three things you need. And every generalized linear model will have those three things. And you'll see this later. At the end, I'm going to talk about software. I'll talk about SAS and R, but any statistics package that fits generalized linear models, which is really any statistics package. They're very common now, so I think anything would do it. You'll see that the software has you specify, it has a way for you to specify each of these three things, and that's all you need for a standard generalized linear model. Everybody okay with these? Okay. Let's talk a little bit about, actually, let's look at a graph. So we've been doing hard work for a little bit. Let's look at a graph. Let's think about what a graph is going to look like. Let's think for a minute about what this graph is going to look like. I'm going to show you a graph. I'm going to show you a graph of data simulated from a Poisson generalized linear model. The outcome is Poisson. One covariate is age, and a relatively short range of age, not a whole lifespan, but like 0 to 10. I can't remember. It's something like that. And we're going to say the outcome, whatever it is Poisson distributed and a log link. What will this graph look like? I'm going to graph y is going to be the outcome, x is going to be the covariate. What will this graph look like? Tell me some features of it. Okay, well, what possible y values would there be?
Non-negative.
Non-negative, there's one more word.
Integers.
Right, non-negative integers, right? So it'll have a little bit of a stripy look. There won't be anything at 1.5. There won't be anything at 2.3, right? So it'll have kind of a stripy look. What else?
Monotonic increasing with x.
You have to speak up a little bit. I couldn't hear you.
Is monotonic increasing with x?
Yes, monotonic increasing. Okay, so won't go below 0, and it will tend to have an upward trend. Well, actually, monotone increasing or decreasing. I'm going to say, let's make beta positive here. So that will give us an upward trend, right? Larger age associated with larger counts. Doesn't have to be that way, but for this one, I'll make it that way. Okay, what else? What will the mean of this distribution be? It's right there. It's going to be e to the age. And what's the shape of that function? Like this, right? It's curved upward. So it won't be a straight line. It'll be a curve. And that's because of what? Because of the Poisson distribution? No, it's because of the link function, right? The mean of the distribution follows an exponential pattern with x. Okay? There's one more thing about this distribution you'll be able to see. What can you tell me about the Poisson distribution? We know a couple things about it. It's for non-negative integers. There's really only one more thing I remember about the Poisson distribution without looking it up.
The mean and the variance are the same.
Yes, the variance equals the mean. Good. So what does that tell you about this graph? What will the graph look like? It'll be curved, but what else? Well, if the variance equals the mean,
It'll be a smooth curve.
it'll be a smooth, I just didn't hear what you said.
Curve. It'll be a smooth curve.
It'll be a smooth curve, yeah, but what about the graph of the points? As the mean increases, we just said, I think it was Randy just said, I don't have your picture, all of your pictures aren't showing up here, so I'm guessing by voice. I think that might have been Randy said that it's monotone increasing, and then we decided it's curved upward, okay? If the mean's increasing, what can you tell me about the variance? It's increasing, right? So what are you going to see? You're going to see this kind of a curved funnel, right? Looks like, remember those old-timey pictures where you see like a thing full of wheat and it's kind of an increasing funnel-shaped thing? And that's what it's going to look like. Let me show you. Oh, maybe I forgot this one. Oh, after all that, it looks like I forgot it. Let me see if I can find it here. There we go. It's very simple to simulate. And there's some pictures. Ignore this one is just a little bit of jittering just to smooth the edges out. But what you see over here, right? There's your curve.
We don't
There's
see
your,
it.
Gary,
Oh,
we're
I
still
got it.
looking at your PDF.
Sorry. Yep, forgot about that. There you go. Okay, just look at the one over here. Right? There's your non-negative, nothing below 0. There's your curve because of the exponential link function. These stripes, these vertical stripes, are just because I used integer ages. They're not the integer outcomes. But you'll notice there's no dots. The dots are perfectly spaced at integers, right? So that's your vertical striping. And what else do you see? Look at the variance of those points there. It's about 2 or 3 units. Look at the variance of those points. It's about 15 units, right? So the variance is increasing with the mean. Okay, everybody got that? It's a nice picture to keep in mind about why, all the different things that are going on in a non-normal model. Okay, so there's that. Remember the assumptions of linear regression? It's equal variance, independence, normal, and linear pattern. Okay, so we've kind of blown several of these here. Okay, everybody okay? Question on that? I'll post that. Obviously forgot to post that one. Now, let me get back to this one. Okay, everybody okay with that picture? Any questions? So I'm going to talk about exponential families here, just briefly, because you can read about it a lot easier than verbally. So I'll talk about it. This is a big class of distributions. Any exponential family distribution can be twisted around to be written into this format. You've got y times theta. Beta has this piece has only thetas. This piece has only extra parameters. So when you're trying to put something in exponential family form, you twist it around until you get it to look like this. If you can't, then it's not an exponential family distribution. So there are other ways, other forms to write this, but this is the one I found is to be the most useful. I will point out, for those of you who took theory and you saw quite a bit of this exponential family distribution, another way to view generalized linear models is as how to do data analysis with exponential families. Okay, you talked a lot last year about the exponential family distributions. You proved a lot of stuff about them in theory. Did you fit any models with covariates? Did you talk about how to include covariates in exponential families? Okay, that's what I'm talking about today. If you want to do statistical analysis, you have to have covariates, right? All your treatments, your time trends, your covariates, all that stuff. So what I'm talking about today really is how to do data analysis with exponential families. Okay, there may be nuisance parameters, scale parameters. I'm going to jump through some of this pretty quickly because it's getting pretty deep into the weeds, and you're certainly good to read it, but it won't be the focus today. I will step back a little bit and ask, okay, you've seen a lot, you've seen some equations, you've seen some graphs. We're going to talk about estimation, likelihood, maximum likelihood, stuff like that. What are we trying to do with estimation? What is it we're estimating and why? When you do a regression problem, forget about all this stuff. You go back and do a regression. Somebody says, do a regression. What's your goal in regression?
Minimize the error.
Eliminate the error, and estimate what?
The mean.
Not quite.
Estimate the effect of predictors of interest on outcome.
Yes, the effects of predictors of interest on the outcome, which in this model are what? What in this model, any of these models we've talked about here is a good one. What in this model describes the effects of covariates on the outcome?
The betas.
The betas, right? Our whole goal here is to estimate the betas. Okay, that's what we're doing with regression, is estimating covariate effects in these models. Okay. Okay, so here's another great application of your theory class last year. For those of you who took theory, you did all that stuff with maximum likelihood. These models are probability models, so they can just be estimated by maximum likelihood, right? You write out the likelihood, which is the product of all the individual densities. You take its log, and you find the values of betas that maximize that, okay? That's maximum likelihood. So this is a great application of maximum likelihood. You're getting the betas. Your goal is to solve for the betas. Here's the log of it. Again, I'm not going to work through in detail these because I've got some other things I want to talk about. But it is a straightforward application of maximum likelihood. Except it's not a closed form solution. So you don't get an equation that says beta equals, beta hat equals, right? For linear regression. This is okay, so remember I said you learn a lot about linear regression from studying non-normal models? Well, this is one of those cases. One of the reasons linear regression is so hugely important and was developed so much earlier than these models is because it's a closed form solution. Beta hat equals x prime x inverse x prime y. Okay, it's a big matrix calculation, but it's one calculation. So as soon as you have a matrix calculator, you have beta hat. Not so with generalized linear models, okay? Because they're nonlinear, and it's not really the non-normality, it's really the non-linearity. Well, actually, yeah, so it's sort of both, but yeah, okay, sort of both. But the point is, it's not a single value. You have to iterate it, and there's an algorithm which is called the iteratively reweighted least squares algorithm. One of the handouts I posted gives a couple derivations of that. There's a couple different derivations of that, and so one is based on weighted least squares, the other is based on Newton-Raphson. But either way, you come up with an algorithm like this. I'll just give you the overview of it. I think the key takeaway message to remember about this. Okay, by the way, the reason this is important, it is important to understand the algorithms behind these calculations, at least have a pretty good sense of what they're doing. And the reason is because software doesn't always work. And when it doesn't work, it helps to understand what's going on with the algorithm so you can take a guess at least at what might be going on. Here, this is an iterative algorithm. So the way you start is calculate a least squares estimate. So in other words, just fit straightforward linear regression. That's wrong for two reasons. What are the two reasons that'll be wrong? It's not linear, and it doesn't have equal variance, okay? So for those two reasons, standard linear regression will not be correct. Okay, but it's a starting place. Then calculate some variances and calculate some weights and do weighted least squares. Did you talk about weighted least squares with John Rice or any of you in 612? Maybe not, I can't remember if that's covered. Anyway, weighted least squares is a way to take into account different values getting different amounts of weight in the fit. And that's necessary here partly because of the unequal variances and partly because of the curvature. So these weights have terms for both of those pieces. And then here's your beta hat. This looks familiar? Remember beta hat, x prime is x inverse x prime y. The only difference here is the w's, right? You've got these w's, and those are to account for the curvature and the unequal variance, okay? So you get an estimate of beta hat. So why aren't you done? Well, what about the W's? The problem with the W's, and I went through this too fast for you to probably be able to see it. The W's have betas in them. But you're trying to estimate the betas, right? So you're trying to estimate something that involves itself. And this is where the iteration comes in. You get your best estimate of betas, calculate the W's, use those to get a better estimate of beta, use those new betas to get better estimates of the W's, W's to get better estimates of beta. You see how it works? It's this flip-flopping back and forth between these two steps. And that's where the iteratively reweighted, every time the weights change, it's basically least squares. Every time through the weights change, that's the reweighting. And it's done iteratively. That's the iterative part. So the name is really perfect for what it's doing. And you keep that process up until convergence. And you'll see in software, generalized linear software, there will be flags. They'll say, you know, the difference between successive estimates is small enough, or the difference between the -2 likelihood values is small enough that we declare this to be to have converged. Okay. Everybody got the feel for it? Any question on the general flavor of the algorithm? I think the key takeaway is that it's like least squares, but it has to be iterative. But this is, in terms of iterative algorithms, this is a theoretically based one, and it's about as bomb-proof as you get for iterative algorithms. Okay. Any question on that? Okay, so that is the standard way. Any software package that fits generalized linear models will use this algorithm. It is the way to do it. And that's why the Nelder and Wedderburn paper was so great. It went from nothing to a complete solution. It was really a terrific piece of work. We'll talk, when I come back in a few weeks, we'll talk about Markov chain Monte Carlo, which is a Bayesian approach to fitting these same models, extends the kinds of models that can be fitted with this, with these methods. Okay, any question on any of that? I know I blew past it really fast, but you know, when I used to teach a PhD elective on this stuff, I'd go in and there's a handout actually I put in the thing if you want to take a look at the way the algorithms are derived. But I think for what we have, given the amount of time we have, I think what we, you know, what I'm focusing on is data analysis. But like I say, it is important to have a feel for how these algorithms work for when they don't work. Any questions on that stuff? Okay, I'm going to skip this stuff on model fit for today, and I'll come back and touch on it next time. Inference, this is great because we've got a lot of stuff for free, right? You remember how you did all that hard work in theory? Those of you who took theory, you did all that hard work on maximum likelihood, and you proved stuff about walled tests and likelihood ratio tests, and you defined AIC and BIC, all that stuff. That was for any model that's fitted with maximum likelihood. This model is fitted with maximum likelihood. So all of those tools, they're there. Everything you derived in theory works here. There's no new twists, okay? The output prints out estimates, standard errors, walled tests, z-values, p-values, likelihood values. You can construct likelihood ratio tests, AIC and B. It's all there for free, right? So that is, again, one of the super great things about the original paper, that Nelder and Wedderburn paper. It really just laid all this stuff out. There's your walled test, right? Estimate minus true value over standard error, confidence interval, estimate plus estimate minus true value, null value, plus or minus a table value times standard error, right? It's all there. AIC, BIC, no changes at all. Everything's exactly the same. Everybody okay there? Okay, any questions about what I've done? Okay, so we've talked, let's go back to the outline here. Okay, so we've reviewed, sorry, this is day one, talked about the basic theory. We'd spent a lot of time on the models and methods of generalized linear models. I just talked pretty quickly about iteratively reweighted least squares. And in the last few minutes, I want to just briefly talk about these two handouts. There's one on software in SAS and R, and one on interpretation. And the next time, I think I won't quite get to history and references, but we'll do that next time. So let's see, I gotta find yet another handout here. All these are posted, I believe. I think I sent them to Matt last night, so they should be posted here, software. Okay, so these are for, this is a great simple reference. I try to pull everything together. I actually use it all the time because I can't ever remember the syntax either, but let's take a quick look at it here. We've got in SAS, the most standard way to fit these models is proc gen mod, or generalized linear models. Proc gen mod, class variables like usual, and then here's your model. Here's the guts of it. And what do you notice? What do you specify? What are you having to specify in that statement?
Those same three components that you pointed out earlier.
Exactly. We've got, and where are they? Where is the random component is Poisson.
Mhm.
The link function is log. And what else? The
Your predictor.
systematic, good, exactly. Yeah, the systematic component, there's all your covariates and stuff, okay? So you've told all three pieces of that algorithm, you've fed in that information, you have fully specified that, okay? For binomial, it's the same thing. I will point this out, like with a big, I should have put this in like gigantic, bold, red print, because it's very easy to misunderstand. Y/n does not mean y divided by n, okay? If you were going to calculate a binomial proportion, you would take the number of events divided by the number of trials, right? But that's not how you fit the model. You don't, to fit this model, you don't do that calculation and then fit the model. If you do that calculation, you have numbers. You don't have any, you don't have your denominators, you don't have counts anymore. So you can't do this that way. This means y is the number of events, n is the number of trials, okay? So that's just the syntax, but that's what that means. Here you go again. Covariates, distribution, and link function. You can use proc and now mix, which is nice if you need to extend this model to other situations. This is a nice way to do it. What will you notice here? There's your covariate piece, there's your link function, and there's your random piece. Same three components, okay? You come down to R, and R, the most common way is GLM. There's your covariates, there's your distribution, and there's your link function, okay? Everybody okay with that? So the software is straightforward for these, and you do have to specify those three components. Any questions on that? And you will be using, for your homework, you'll be using this software. I don't remember if I specified which one, but you'll be using one of these two pieces of software to fit some models to the serial data. And I think the homework's posted in there. So I'm going to do one last handout here. which is yet another cool thing about generalized linear models. Now you can see I'm making Matt look really good. I bet he doesn't have any of these beautiful handwritten handouts. Okay, so we're interpreting covariate effects, which means we're going to talk about using the betas in a sentence. That's the goal here, right? We need to use betas in a sentence. Okay, and really, it doesn't have much to do with the distribution. Well, this is all about the link function. Interpretation of betas is all about the link function. Because remember I said before that the key thing that the link function is doing is specifying the scale of your analysis. Okay, basically log, logistic, or linear are the ones I've looked at here. Okay, in linear regression, there's your mean, beta 0 plus beta 1 times x. Just look at 1x here. There's your nuisance parameter there, but we're not going to involve that. Each additional unit of x is associated with an increase of beta 1 units in the mean of y. Okay. There's nothing new there. I'm just pointing that out. And you can derive that by the expected value of y given x plus 1 minus the expected value of y given x. Everything subtracts out except the beta 1. And that's how you derive that. Everybody okay with that? Okay, nothing new there. For the log link, say in a Poisson regression, each additional unit of x is associated with an increase of a factor of e to the beta 1 in the mean rate of y. Okay, so let me point out a couple things here. It's all about the link function. And you'll remember, we had talked about possibly using a transformation for Poisson data because we thought it might be skewed. We're still using a transformation, right? We're still using the log transformation. The difference is we're using it on the mean of the distribution, which is a parameter. We're not using it on the observations. That's the key. If there's a single key idea for generalized linear models, that's probably it, is that you're transforming in the parameters, not the observations. Okay? So there's a factor change, and you derive that in the same way. Y given x plus 1, divide by now y given x. Why do we divide instead of subtract? Above we subtracted, and here we divide. Why do we do that?
It's a rate.
What's that?
Because it's a rate.
Because it's a rate, that's correct. But if we didn't know that, there's another even more either fundamental or cynical, I'm not quite sure, but practical, that's a good word. It's the more practical reason, because it works, right? If we use subtraction on a model with a log link, what happens? All this stuff doesn't cancel out, right? So with a log link, with a linear link, we have to subtract. With a log link, we have to divide, okay? And it's not that you couldn't use it, it's not that you couldn't subtract, it's that you'd get a bunch of beta zeros and x's over here, okay?
Aren't you still subtracting, but it's just the properties of logarithms that a log minus a log is a log over a log?
And that would be another way to look at it. You could look at it that way. So you're subtracting on the linked scale. Yes, you could look at it that way. Yep. Okay, but the point is, we're doing what works here to give us a nice interpretation. And the point is, this is just beta 1. So we now have a covariate effect that holds over all values of all the other covariates. For all the other covariates fixed, see, they have to, if there's other covariates in here, they have to be fixed, and then they'll divide out. Remember, this is the interpretation of an adjusted association. For equal values of all other covariates, the effect of x1 is is a factor of e to the beta 1. Okay.
Is that a good stopping point? I'm just going to stop the recording, Gary.
Yeah,
want to make a few follow-up comments. That's fine. I just need to jump on another Zoom call.
Sure, no
on my
worries, Matt.
computer, so.
Yeah, go ahead.
Okay, I'll just stop the recording. Then.
Yeah,
Thank you.
sorry guys, I try to hit this.